Today, we're talking about something truly wild, a plan to put a fully functional nuclear reactor on the surface of the moon by 2030. And this isn't just about keeping the lights on at a moon base. This is about building the power grid for our entire future in space. So, to really get why we need to go nuclear on the moon, you have to appreciate just how brutal the environment is. It is a world of insane extremes. For 2 straight weeks, the surface is scorched in sunlight, hot enough to boil water. But then, it plunges into a 2-week night, a deep, dark freeze that is colder than anything on Earth. Trying to survive that, it's a total energy nightmare. And that right there, that 14-day night, is the single biggest roadblock for NASA's Artemis program. The whole goal is a permanent human presence. So how do you do that when your main power source, the sun, just completely disappears for half the month? Solar panels are great, but here they become totally useless. Right? Because you can't just tell the astronauts to, hibernate for 2 weeks. Life support has to run 24/7. Critical science experiments can't be interrupted. And if we ever want to do the cool stuff, like mine for water ice in those permanently dark craters, you need power that is constant, totally reliable, and does not care one bit about the sun. So, the solution is nuclear. And I know, that might sound super futuristic or even a little scary, but the idea of using nuclear power in space, well, it's actually built on a long, very successful history. This isn't some brand new, untested idea. It's a proven technology that's been behind some of our greatest moments of exploration. For decades, our deep space probes have run on something called an RTG, a radioisotope thermoelectric generator. The easiest way to think about it is as a nuclear battery. It's not a reactor. It just takes the gentle, steady heat that comes from the natural decay of a plutonium pellet and turns it into a small but incredibly dependable trickle of electricity. This is the magic that's kept the Voyager probes alive in interstellar space, and it's what's powering the Perseverance rover on Mars as we speak. But here's the catch. An RTG, for all its amazing reliability, only puts out a few hundred watts. That's enough to run a science instrument, maybe a light bulb. But a lunar base, with habitats, life support, rovers, and industrial equipment, you need tens of thousands of watts. It's a totally different league. And to make that jump, you have to go from simple radioactive decay to full-on nuclear fission. And that brings us to what we're talking about today, the modern solution, a small, compact fission power plant engineered from the ground up to work on the moon. So what exactly is nuclear fission? Well, it's the very same process we use in nuclear power plants here on Earth. The basic idea is actually pretty simple. You take a heavy atom, like uranium, and you split its nucleus. When you do that, it releases an absolutely enormous amount of energy as heat. The way this little reactor works is actually quite elegant. It all happens in 3 steps. First, you get a controlled chain reaction going, splitting uranium atoms to create intense heat. Second, that heat gets transferred to super efficient Stirling engines, which are amazing at turning heat into motion. And finally, that motion spins a generator, which produces a nice, steady stream of electricity. Now, this first reactor is designed to produce 40 kilowatts of power continuously. So what does that mean? Here on Earth, that's enough to power a few houses. But on the moon? It's a game changer. It's enough to run a habitat for a crew of astronauts, keep all their life support humming, power a whole suite of science gear, and recharge rovers. And the best part? It can do that for at least 10 years straight, without ever needing to be refueled. Okay, I know what you're thinking. The moment you say nuclear, the first question is always about safety. And this thing has been designed from the very beginning with safety as the #1 priority. It uses low-enriched uranium, not the stuff you'd use for weapons. But here's the most important part. It's launched cold. It is completely inert, totally turned off. It's not actually activated for the very first time until it is safely on the surface of the moon, 250,000 miles away from Earth. And listen, this isn't just some drawing on a napkin. This is a real mission. It's got a roadmap, it's got a budget, and it's got a deadline. NASA and the Department of Energy are working together to make this happen by 2030. You can actually see the momentum building over the last few years. It really kicked off back in 2018 with an experiment called Krusty, which proved the basic tech worked. Then in 2022, NASA got major industry players involved to start drawing up real designs. And now, with the official partnership between NASA and the Department of Energy locked in, it is all systems go for deployment in 2030. And the people at the very top are completely on board. NASA Administrator Bill Nelson put it plainly. He said achieving the future we want in space requires harnessing nuclear power. He doesn't just see this as a utility, he sees it as the key that's going to unlock a whole new golden age of space exploration. This is foundational stuff. And that vision is shared over at the Department of Energy. Assistant Secretary Catherine Huff called this project's goal one of the greatest technical achievements in the history of nuclear energy and space exploration. That really tells you something, doesn't it? This is seen as a massive breakthrough for both of those fields at the same time. So why all this fuss over one little reactor? Why does it matter so much? Because having abundant, reliable power on another planet, it changes everything. It's the difference between just visiting a place and actually learning how to live there. And this is where it gets really, really exciting. This one piece of technology unlocks the next chapter. We're talking about permanent habitats. We're talking about starting a lunar industry, like literally pulling oxygen out of moon rocks, powering whole fleets of rovers, and maybe most importantly, it's the perfect test bed for the kinds of nuclear systems that could one day get us to Mars way, way faster. And let's be real, there are huge geopolitical stakes here too. We are absolutely in a new space race. Other countries, especially China and Russia, have their own plans for lunar bases, and those plans also include nuclear power. Being the first to establish this capability gives the US a massive strategic advantage when it comes to accessing and using the moon's resources. But when you zoom all the way out, that's what this is really about. This isn't about planting another flag. It's about figuring out how to live and work and build a life on another world. It's about laying the literal and figurative foundation for humanity to become a multiplanetary species. It just leaves you with this amazing question. Once you solve the power problem, so many other limits just melt away. So what will we build? What will we discover? What do we become when we have virtually unlimited power on a whole new world? The possibilities are just getting started.